Okay friends, welcome back. Today we are going to discuss about circuit examples. There are two circuit examples, number one LC oscillators and number two ring oscillators. So LC oscillators having derived expressions for phase noise at low and moderate offset frequencies, it is instructive to apply the insights gained to practical oscillators. The popular Colpitt's oscillator and its relevant waveforms are shown in figures. An important feature is that the drain current flows only during a short interval coincident with the most benign movements. For example, Colpitt's oscillator is shown in the figure. So, approximate incremental tank voltage and drain current for Colpitt's oscillator is like this. Its corresponding excellent phase noise properties account for the popularity of this configuration. Next, it has been known that the least phase noise occurs within a certain narrow range of tapping ratios, capacitance, etc. A common configuration that does so is Clapp's modification to the Colpitt's oscillator. A common configuration that does so is Clapp's modification to the Colpitt's oscillator as shown in the figure. Clapp oscillator and Colpitt's oscillator, both circuits are given in the below. So, differential implementations of oscillators with tapped resonators have recently made an appearance in the literature. These types of oscillators are either of clap configuration or the dual. So, the clap configuration becomes increasingly attractive as supply voltage scale downwards. So, where conventional resonator connections lead to VDD constrained signal swings, use of tapping allows signal energy to remain high even with low supply voltages. So, VCO in Margaret L. Simplified schematic of the VCO in Margaret L. A simplified schematic of this oscillator is shown in the figure. A tapped oscillator is used to increase the tank signal power P signal. The optimum capacitive tapping ratio is calculated to be around 4.5 based on simulations that taken into account the cyclostationarity of the noise sources. Ring oscillator. 5-stage ring oscillator with identical noise sources on all nodes. First, the resonator Q is poor because the energy stored in the node capacitances is thrown away every cycle. Hence, if the resonator of a Colpitt's oscillator may be likened to a fine crystal wine glass, the resonator of a ring oscillator is mud. Next, energy is restored to the resonator during the edges rather than at the voltage maximum. As a consequence, ring oscillators are found only in the most non-critical applications or inside wideband PLLs that clean up the spectrum. Phasors for noise contributions from each source. E power j 2 pi by 5, 4 pi by 5, 6 pi by 5, 8 pi by 5. To understand the effect of this correlation, consider the special case of having identical noise sources on all the nodes of the ring oscillator as shown in the figure. If all the inverters in the oscillator are the same, then the impulse sensitivity function for different nodes will differ only in phase by multiples of 2 pi by n as shown in figure. The total phase resulting from all the sources is given by phi of t is equal to minus infinity to infinity h of phi t comma tau I of tau d tau is equal to 1 by q max of minus infinity to t tau omega naught of tau I of tau into d tau. So from the superposition, we have already known that phi of t is equal to 1 by q max minus infinity to t I of tau n is equal to 0 n minus 1 tau omega naught tau plus 2 pi n by n d tau. Expanding the terms in brackets in a Fourier series, we observe that it is 0 expected at DC and multiples of n omega naught, that is phi of t is equal to n by q max in n is equal to 0 to infinity c of n minus infinity to t I of tau into cos of n omega naught tau into d tau, which means that for fully correlated sources, only noise in the vicinity of integer multiples of n omega naught affects the phase. The derivation of approximate analytical expression for ring oscillator ISF. An approximation for the an approximate expression for the ISF as depicted in the figure. The ISF is approximated to two triangles as shown in the figure. The RMS value of the ISF is given by tau's gamma square RMS is equal to 1 by 3 pi into 1 by f dash rise whole power cube into 1 plus a cube, where f dash of rise and f dash of fall are the maximum slope during the rising and falling edges, and where a is the ratio of f dash rise to f dash fall. What are the radio architectures? GSM radio architectures, CDMA radio architectures, and UMTS radio architectures. So, first of all, what is GSM radio architectures? GSM, Global System for Mobile Communication, is a digital mobile network that is widely used by mobile phone users in Europe and other parts of the world. So, GSM uses a variation of the time division multiple axis and is the most widely used of the three digital wireless telephony technologies, TDMA, GSM, and code division multiple axis. So GSM digitizes and compresses data, then sends it down a channel with two other streams of user data, which in its own time slot it appears at either the 900 MHz or 1800 MHz frequency band. Global System for Mobile Communication is a globally accepted standard for digital cellular communication. GSM is the name of a standardization group established in 1982 to create a common European mobile telephone standard that would formulate specifications for a pan-European mobile cellular radio system operated at 900 MHz. It is estimated that many countries outside of Europe will join the GSM partnership. If you are in If you are in Europe or Asia and using a mobile phone, then most probably you are using GSM technology in your mobile phone. It is widely used mobile technology across the world. GSM stands for Global System for Mobile Communication. It is a digital cellular technology used for transmitting mobile voice and data services. So, important facts about the GSM are given below. The concept of GSM emerged from a cellular based mobile radio system at Bell Laboratories in the early 1970s. GSM is the name of a standardization group established in 1982 to create a common European mobile telephone standard. GSM is the most widely accepted standard in telecommunications and it is implemented globally. GSM is a circuit switched system that divides each 200 kHz channel into 825 kHz time slots. GSM operates on the mobile communication bands 900 MHz and 1800 MHz in most parts of the world. In the US, GSM operates in the bands 800 MHz and 1900 MHz. So GSM owns a market share of more than 70% of the world's digital cellular subscribers. GSM makes use of narrowband time division multiple access technique for transmitting signals, and also GSM was developed using digital technology. It has an ability to carry 64 kbps to 120 mbps of data rates, and presently GSM supports more than 1 billion mobile subscribers in more than 210 countries throughout the world. GSM provides basic to advanced voice and data services, including roaming service. Roaming is the ability to use your GSM phone number in another GSM network. GSM radio architectures and its milestones. In 1892, first of all, GSM was formed. 86 field tested. 1987 TDMA chosen as its method. 88 Memorandum of Understanding signed. 89 Validation of GSM system. 90 Pre-operation system. 91 Commercial system startup. 92 Coverage of larger cities airports. 93 Coverage of main roads. 95 Coverage of rural areas. 96 June 133 network in 81 countries operational. 97 July 200 network in 109 countries operational. Around 44 million subscribers worldwide. 99 Wireless application protocol came into existence and became operational in 130. So 96 June 133 network in 81 countries operational. 97 July 200 network in 109 countries operational. around 44 million subscribers worldwide. Wireless application protocol came into existence and became operational in 130 countries with 260 million subscribers in 99. 2000 general packet radio services came into existence. 2001 May over 550 million people were subscribers to mobile telecommunications.